Right, good afternoon. Welcome to a bit of British weather. Right, so we got through sort of a basic bit on vibrational spectroscopy. We've done so far everything in terms of harmonic oscillators, and I sort of said to you that I don't actually do it that way. So I thought I'd spend a little bit of time just saying what we actually do. So to calculate a line list, so a list of all the different transitions that may occur, and I'm going to keep this as simple as possible case, one potential energy curve, one coordinate, so diatomic. So you get a curve looking something like this. So you should be vaguely familiar with these potential energy curves, Morse curves or whatever, with a standard thing where they have a minimum at the bottom, dissociation out here, hard potential wall here. Just to remind you why the harmonic oscillator approximation really is an approximation. Because if you did this with a harmonic potential, it would look something like that. So at the bottom, it's not bad. Probably not quite as good as I've drawn it, actually, but at the bottom it's not bad, but it's too soft at the short range, and it doesn't dissociate at all. It has an infinite number of vibrational levels, whereas at least for things not charging to ions, you get a finite number, normally quite often not very many. Hydrogen has 14, for example. And actually, from a theoretical point of view, which worries me, if you actually extrapolate this up here far enough, you go out of the domain of the problem. You go through zero, and that's a problem actually more for polyatomic systems than diatomic systems. But it's quite easy in a polyatomic to go out the domain of the problem. So we don't use that. So I'm going to tell you what we do use. So this is, for instance, sodium chloride, something with a nice big dipole. So the first thing you have to do is to worry about the electronic structure of the problem. And there are well-known packages available for calculating electronic structure. I know I've spoken to a couple of you about this. We use quantum chemistry codes or electronic structure codes. The most famous one is called Gaussian. For those of you who know, I run a company called Quantumol. In many ways, Gaussian was our inspiration for doing Quantumol. It was founded by British scientist John Popel, who won a Nobel Prize. Let's get this in right order. He founded Gaussian. Gaussian became very popular. Gaussian fired him, and then he won a Nobel Prize. At which point Gaussian probably regretted having fired him. But all I've done is the first step. I founded a company to make our programs easy to use. That was the idea of Gaussian and John Popel. But Gaussian is a bit weird. It's very slow. And if you publish timing figures showing how much quicker another program is than Gaussian, you get banned from using Gaussian. And there used to be, I don't know whether it's still, there used to be a web page called Banned by Gaussian, which had every famous quantum chemist list on it. It was a matter of pride amongst quantum chemists to be on the Banned by Gaussian list. Anyway, let's forget that. You need an electronic structure code. We use one called MolPro. That's a commercial code, but there are things like Orca and Psi4, which are freeware, just a bit harder to use. So you can do couple clusters. I wasn't going to get into, so for a curve like this, couple clusters actually work quite well. So couple clusters is good for a case where you have a single configuration roughly representing the state. If you start doing electronic states, that becomes difficult, and we use multi-reference configuration interaction. There are people, there's a annual meeting in the US in Florida, Sanibel meeting it's a quantum chemistry meeting, but it's basically run by Rodney Bartlett, who's a sort of aficionado of a couple of clusters. So it's a couple of clusters meeting, and I went there 2.5 years ago and told them some of the problems they had, and they all told me a couple clusters equations of emulsion, solved all these problems. And I said, great, well, this is what I need, this is what I need, this is what I need. I never got any of it. And I assume that though it's good, it's not actually that good. So for ground states, coupled clusters is quite often the gold standard method. But I wasn't going to get into technicalities of what we use. We just solve the electronic Schrödinger equation to get, and you get two things from that. You get an energy level, which is one of these dots, and we don't normally do quite as many points as there are dots here, otherwise it gets expensive. Typically, if you're doing a big multi-dimensional system, we may be 10 or 12 points in each degree of freedom. For a diatomic, which is cheaper, maybe we'll do 20, 30, 40. There's probably about 200 dots there. So that's a bit overkill. And you get an energy, and you get a wave function, and with the wave function, you can generate a dipole. So I haven't drawn the dipole on here, but the dipole will vary as a function of geometry, so you get that at the same time. So that's the first step of the calculation. Now, in principle, particularly if you have a lot of dots like that, you don't need to do anything at this point. You could use those dots to solve the nuclear motion. In practice, sorry, I actually didn't revise what's my next slide. Oh yeah, the next slide that's the dipole. So a dipole may look something like that. It's not normally quite a straight line. It was absolutely a straight line. And I've just read a paper which told me dipoles are all straight lines in near equilibrium. Then by definition, all your overtone bands would have zero intensity because fundamental, as I said this morning, is the first derivative, the other ones are the second derivative, third derivative, fourth derivative, and it was literally a straight line. They would all be zero, and they're not. They're not strong, so it doesn't bend much, but they do tend to have a bit of structure. Okay? So you get the dipole at the same time, again, point by point by point. So the next thing is you want to turn that into a curve. So you can compute on the points, but for reasons I'll come to in a minute, it's much easier to fit it to some functional form. So obviously I could fit it to a harmonic oscillator. I don't, for reasons I've already said. We can fit it to a Morse curve. When we're desperate, we fit it to a Morse curve. If we have very little information, we fit it to a Morse curve because a Morse curve only has three parameters: RE, dissociation energy, and one other parameter. So you can normally get that very easily. But normally we use other more complicated. There are two variants of Morses called EMOs, extended Morse oscillators, and MLRs, Morse long range. Now, I'm not going to get into technicalities, but they're just more flexible than Morse curves. In practice, a Morse curve is too hard here. It should be softer. So it's a good approximation, but for getting real accuracy, it's not quite right. So you normally fit it to some functional form of your choosing. And I'll talk in a minute, I think it's in here, it may be in a different set of slides, about our code duo that we use for solving it. And it will do a grid. It will do certain given functional forms automatically. If you have some other functional form, you can always turn it into a grid by simply evaluating it at a number of points. We then use a variational method. Do people know what the variational principle is in quantum mechanics? Someone was talking to over dinner said they knew it classically. In quantum mechanics, is extremely powerful. Basically, it says if you solve a problem variationally, you get an upper limit to the right answer. And that means, and quick caveat, CCSD is not a variational method. So everything I'm about to say doesn't apply to CCSD because it makes approximations. We use an exact Hamiltonian and a basis set where we try to precisely evaluate the integrals, and you take a guess, and if you make another guess and it's lower in energy, that guess is by definition better. You can define better, and you can converge your results. And the practice you do that is, we were all talking about matrix mechanics with Heisenberg, we make matrices. So we develop big matrices, basis sets, we turn them into a matrix, we diagonalize the matrix. And the way the variational principle is normally taught is in terms of ground states. So it says that your best guess energy is an upper limit for the ground state. The reality is if your matrix, if your energy levels, or the eigenvectors of your energy levels are all orthogonal to each other, they're all upper limits to all the states. And you have a matrix that's automatically satisfied. So if I have a 1,000 by 1,000 matrix, in principle, you get estimates for 1,000 states. In practice, they get worse and worse and worse as you go up. So you may get good estimates for maybe 20 states or something, but we just make the matrix big enough to get enough states. So I don't know how many I've drawn here, maybe about 20. And we make a matrix, maybe a few hundred by a few hundred, diagonalize it, and effectively we solve this thing exactly. In fact, we wrote a paper about 2 years ago comparing the convergence of this with a different program. So this is Duo I'm talking about, which is our diatomic program, with Level, which is someone else's program written by a guy called Bob Leroy. And we found that his method converged linearly with the size of the problem he solved. He actually solved the problem by directly integrating using a Numerov method, giving direct integration. We use a basis set. Our basis set is quadratically convergent. His is only linearly convergent. So actually, when you want to get very high accuracy, it makes a very big difference. Ours was spectacularly faster at converging, but they both gave the same answers for a given problem. So we solve the nuclear motion problem, get vibrational levels looking like that. The next thing you do is compare your energy levels with experimental ones. Now I have to make a slight caveat here. You never measure an energy level. You measure transitions between energy levels. So whereas I say we compare with energy levels, I'll tell you in my big lecture how we get energy levels, but sometimes you just compare with transitions. You can do it, it's just messier. It's easier to compare with energy levels because it's 1 by 1, a transition is 2 numbers. The results are normally good, but not good enough. On the scale of the ammonia picture I showed you, it's probably the same. But experimentally, you measure these things to 9, 10 significant figures. We can probably compute it ab initio to 6, on a good day 7. And the astronomers want it 1 part in 100,000. So we need basically to improve on the straight ab initio. H3 plus, when I showed you the results, that was ab initio. H3 plus you can do ab initio because it's 2-electron system. You can solve it really well. But you do vanadium oxide, the ab initio results stink, frankly. And so you're really struggling to get good answers. So the next thing is we compare with the measured experiment. We say, well, it's quite good, but we need to improve it a bit. So we then have a procedure whereby we compute the potential, look at the energy levels, compare the experiment, change the potential. So if the energy levels are too low, we need to make the potential narrower. If they're too high, we need to make it wider. So we fiddle with the potential until they match the experiment. And has anyone here ever heard of something called the Hellman-Feynman theorem? I don't know how much quantum mechanics you guys have done. Anyone heard of Richard Feynman? Yes, okay. So from my area of science, this is his contribution. I mean, I know he invented quantum chromodynamics and high-energy physics treatments, but from the point of view of working on atomic and molecular problems, he invented the Hellman-Feynman theorem, which actually allows you to evaluate differentials of operators in a very cheap fashion. So we do this as well, so we get not just the difference between the energy levels, we get the gradient of the difference between the energy levels, which tells us how much to change things by. My first ever potential fits didn't use the Hellman-Feynman theorem for technical reasons I won't go into here. And they were incredibly slow and computer intensive. Then we discovered this, and suddenly it saved an order of magnitude, more than an order of magnitude in computer time. So we do that, and what I've got here, and it just looks a bit blurry, but I've meant to got red lines and black lines to show that we change things slightly by fitting them to experiment. You then get your final, use that new potential to give you a final list of energy levels and wave functions. The time in this process, well, it goes into two things. One is getting a good ab initio calculation, That depends on the molecule. That may be completely straightforward if it's a simple molecule. It may be a lot of work. If you're vanadium oxide, we wrote whole papers on the subject of how difficult it was to get good ab initio calculations for vanadium oxide before we even got the right answer, or a good enough answer to work with. We never got the right answer. We still don't have the right answer. So you get your final vibrational energy levels, and then you get a list of transitions. So at the moment, these transitions are just wave numbers saying 2038 or 3000 and whatever. But you also need intensities, but I'm going to have a pause at this point. I put a note in, sorry. Let's go backwards. I put a note in here with a blank sheet, and that's bad news for you because that means I'm going to draw all over it. You're going to have to try and read my striping. So, wave functions of a harmonic oscillator. Anyone know a good example of a classical harmonic oscillator? Yep. Okay, yep. So swinging like that, you mean? Oh, on the table, okay. Yeah, okay. Pendulum also. So I like to think of a pendulum like this. But you're right, there are lots, and the one you had as well is also a good example. So a pendulum is a harmonic oscillator. We put the harmonic potential in here. Looking like this. Where does a pendulum spend its time? If you had a photograph which took a photo every microsecond or something of a pendulum doing this, where would be the biggest probability of seeing the pendulum? So a pendulum, and because it's classical, let's say at this energy, you have a distribution looks like this. Because it goes very fast through the middle, very slow at the ends. So it does this. So if you actually took, you don't normally do classical mechanics in terms of probabilities, but we're going to do quantum mechanics, so it's good to think about. Okay, so it would look like that, with the biggest probability at the turning points, and of course it doesn't go outside the turning points, because that's a classical turning point, and if you're classically, you can't do it. So that's what a pendulum looks like, or a classical harmonic oscillator looks like. A quantum harmonic oscillator I'm not going to do all of these. So what do you think a quantum harmonic oscillator looks like at the top end, at the very high energies? Any suggestions? What's it look like? So there's something called the correspondence principle. That means anything to you? I think that's one of the things in Heisenberg's 1925 paper he considers the correspondence principle. Correspondence principle says basically as you get either high energy or high mass, you should just tend towards the classical result. So high energy, the probability distribution, and I'm going to actually deal in wave functions in a minute, so the square root of probability distribution, but let's just keep with probabilities for a moment. Will look like this. It will look classical. Okay? Anyone know what it looks like down here? And I think you do, because half of you gave me that answer for the pendulum in the first place. Yeah. Do that again? Yeah, exactly. The ground state probability distribution looks like that. So it's completely different from the classical one. It's centered around the middle. And it goes towards the classical one. So I'm going to do a third thing here. These are probabilities. And I'll draw one more in here. That's the first excited state probability. But then now let's do wave functions, because we're going to need wave functions. So as you should know, I'm doing this backwards because the probability is the square of the wave function. If you try taking the square root of the probability, you lose phase information, so it doesn't quite work. So the ground state still looks like this, but notice, importantly, compared to the classical, you get a little bit of tunneling outside the classically forbidden region. The first excited state has to be orthogonal to the ground state. So it has a node in the middle. So these two bits are symmetric, or anti-symmetric, should I say. They're the same, but different sign. And if you put it overlap with that, you get 0. The second excited state looks something like that, and these are not meant to be asymmetric. I'm just not very good at drawing. So it has 2 nodes. So the number of nodes, if you remember, this was v equals 0, v equals 1, v equals 2. So the thing has v nodes in it, in each of these wave functions. So you have one more node in each wave function, and that in short, and they're done to design that if you take an integral actually, let's do this differently. The design that if the wave functions are not the same, they're orthogonal when you take the overlap between them. Okay? When you go right up the top end, you get something like that. Lots of nodes, biggest amplitude at the edges, maybe a very, depending if you're really at the top end, there's no tunneling into the classical region, but probably a little bit of tunneling into the classical region. But basically you tend to this, well, you tend to the square of that tends to this. The reality has little ripples on it because it's not completely constant. Now this is important for something we're going to do tomorrow when we look at electronic structure. We're going to consider something called the Frank-Condon approximation. So when we look at not electronic structure, electronic transitions, sorry, the vibrational distributions are given by the Frank-Condon approximation. Now Frank and Condon developed this model for vibrational processes, but actually it's used for all sorts of other things. So if you do, for instance, electron collision, electronic excitation, you can use the Frank-Condon approximation. I had a project for a while looking at radioactive decay of tritium molecule to give you a rather strange helium-3 T+ molecule, and we use Frank-Condon type approximations for mapping the vibrational states onto it. So it's a widespread approximation. I'll go through it tomorrow, but you need to understand these wave functions to have any idea, any chance of understanding the Frank-Condon approximation. Because basically it goes on overlap between wave functions between different electronic states. Okay, so that was, we've got our transition frequencies or wave numbers, and we have our vibrational wave functions. So with our vibrational wave functions, sorry, I need to remember to do this. With our vibrational wave functions, we calculate the transition intensity. And I've already seen the first mistake on this page, and there may be more than one, but there's certainly one. So let me correct the mistake. And I didn't mean to do that. Yes, I didn't mean to do that. No, I didn't mean to do that. It's funny because I've cut and pasted that equation from somewhere. But it is definitely wrong. Because I've already told you that everything's always squares of dipoles, and there's no squares of any dipoles in there. So I think that's the correct definition of the line strength. So I think what we're missing is that. It depends on the square of the line strength. So this is a transition dipole. It takes the final state and the upper state. It doesn't matter if you transpose them, they're real, so it doesn't make any difference if you take them the other way around. Integrated over the dipole. So if you remember our wave functions that I was just drawing, if you want to go from the ground state, which looked like that, to the first excited state, which looked like this, even if the dipole was finite but completely flat, you would get 0. It's only the slope. So I told you it depended on, this transition dipole depends on, sorry. For the fundamental, which this is the fundamental transition, it depends on the slope of the dipole. As I said, if it was completely flat, you'd get nothing. However, if you go for a pure rotational transition within a vibrational state, then you can see that the vibrational state in the bra and ket are the same. So you just get a vibrational average of the dipole. So we calculate the dipoles. And the good news is, for simple molecules, we can do these incredibly accurately. In fact, somewhat to my surprise as a theorist, I find myself being funded to do metrology. Metrology is the study of highly accurate measurements for determining fundamental properties. And it turns out that transition intensity is very important for things like defining Boltzmann's constant. They're also important for things like remote sensing of temperature and pressure. And there are a few labs, well, it's European money we get, but one of the labs is in America and one in China, but there's several in Europe. And they make very accurate measurements, maybe of 1 or 2 lines. Another lab makes very accurate measurements of 1 or 2 lines, but they're not the same lines. And it turns out if we calculate them all, everyone then compares to our calculations, and our calculations, we can develop models which basically go with an experimental accuracy. And the difference here is that typical, not really high-class experiments are good to about 1%. So a standard lab experiment that fills up large amount of data in databases gives you transition intensities to 1%. We can do 1%. We can do better than 1% in good cases. It's not like the lines where we're talking about 8, 9 figures, 10 figures needed. So it's a difference of the accuracy. So we get something called a final line list. And for some reason, I don't quite understand, I had a picture of that in my first slide and we skipped over it. So I'm in my first talk, so I may go back and get it up. So we store our data in 2 ways. We store a states file, which is the energy levels with quantum numbers, uncertainties, lifetimes of states, and things like this. And then the main thing we store here is the Einstein error coefficient. And one minute. Let's do this the way around. So if you have a system in state I, initial state, and you consider all the possible final states, the lifetime is simply given by the inverse of the sum over all the transitions to final states. So this is essentially a half-life, just like you get in radioactivity. So this lifetime says, if I have a molecule in this excited state up here, or an atom in this excited state up here, in the time given by Tor there, half of the species will have decayed radiatively. So it's the same as if you have a radioactive atom within the half-life, half the species will have decayed. So I like Einstein error coefficients because they have rather nice units. Seconds to -1. So you can interpret those, you just flip them the other way up, and they're a lifetime, gives you some physical information, and also no one debates time units, so just seconds to -1. There are at least 6 other ways of doing transition intensities. I'm not going to mention it. Well, we may get into high tran ones occasionally when I show pictures, but they're best avoided. These are the simplest you can use. And you'll notice that the Einstein A coefficient depends on the cube of the transition, which means that if you have two very nearby transitions, they get quite small. And you also get, the other problem is that if you have two levels close together and they're emitting, you also have to consider self-absorption. So that you have to balance the fact they may be emitting against absorbing. And you see that actually in some astronomical spectra. For instance, it's not unusual to have if you look at very high resolution, it's not unusual to have an astronomical line that looks like that. And that's just one line. No isotopes, no funny things. What's happening here? You've got something which is absorbing the line in the middle, absorbing the middle of the line where it's cold. So you've got a hotter object going out cooling, and it emits in the middle. So originally emits looking like this, and then the middle bits gets absorbed further out where the system is colder, and you can get the things going back up again. This line shapes can give you a lot of information from this sort of thing. So I'm going to talk more about the XMOL project in my last lecture, and also why we're doing it and how it matches the observations. But just to give you a few bits and pieces, sorry, I'll keep on forgetting to do this. So this is actually a map of what I tried to go through slide by slide. You start off with the ab initio electronic structure calculations. You obtain potential energy surface or a potential energy curve. It's a curve for a diatomic. It's a surface if you've got more than two atoms. You take the dipole moment surface, DMS. Not quite sure why this is quite so knotted here, but anyway, you take the potential, because you do nuclear motion calculations, you get energy levels, you compare the energy levels, energy levels here, you compare the energy levels with the experiment. If they're not good, you go back and do the potential, you do the variational calculations, you do this. This can be quite a laborious process. At one point we had a water potential called H2O 365. That was not to do with the number of days in the year, it was because it was the 365th attempt to solve this problem. We don't normally go quite that long, but it does give you an illustration that you can spend a long time doing this. Then when you've got a nice surface, you do this calculation, you keep the wave functions, you keep the energies, you have the dipole that you saved in the first place, you compute your Einstein A coefficients, you get a line list, and I will go back and show you what this looks like. And I think it was in lecture 1, wasn't it? And I'm not quite sure why it was in lecture 1, but I think it was. Yeah, there it is. So this is the states file, and I've decided obviously not to take any prisoners here. I'm doing a tetratomic molecule, so it's rather complicated. But the general structure is quite simple. First line is simply a counting number. So this starts with the 4,770th entry in the thing. The second line is the energy, and you can see by 4,700 we're already quite high in energy. 18,000 wave numbers. The third line is the total degeneracy. So that's 2J plus 1 for the rotation, plus a nuclear spin degeneracy. And we can see here that J is 0 for this all these ones here, actually, just this snapshot. So that gives you a rotational degeneracy of 1, because 2J plus 1 times 0 for J is 0 is 1. So we've obviously got a nuclear spin degeneracy of 8. And that comes from where does it come from? Why have you got 8? You should get 1 and 3 from the hydrogens. And carbon and oxygen, if this is normalized, so I'm going to pass on why that's 8, because that doesn't look right. And then you have various, so this is a symmetry of the total wave function. This is the K projection, remember, on the Z-axis. There's a symmetry of the rotational wave function, and then vibrational quantum numbers here, N1, N2, N3, N4, going up and actually done in 2 different ways. And I realize this is quite old, because actually more recently we have an uncertainty here. We realized, and when I talk on Friday, I'll explain why we suddenly realized we weren't telling people which of our lines were accurate or not. We knew which of our lines were accurate, but we weren't telling people. So we added uncertainty. We also added a lifetime for reasons I won't dwell on, but it's quite useful. So that's the states file. They're quite big, but they're not huge. What is huge is the trans file. So that's why the trans file is written in a very cut down format. So it's final state, initial state, Einstein error coefficient, and this number here simply refers to this counting number here. So actually you don't even need the counting number. If you've got these in an array, you can just go straight to the array address. So it's saying the final state is state 870,236. The initial state is state 1,057,299, and those you just have to look them up in the list. And these line lists are huge. The one for formaldehyde had billions of transitions in. So this trans file can be gigabytes, many gigabytes long. In fact, we started to put them on Zenodo. Anyone knows what Zenodo is? No. It's a place for storing data for free, but you get a DOI for it. And certainly in the UK, there's a lot of emphasis on storing your data. But they have a 50 gigabyte limit. And we said, we've got lots of files bigger than 50 gigabytes. Can we do more? And they said, if you pay us, you can do 100 gigabytes, which didn't really solve the problem that some of our files are terabytes. So we only have small molecules on Zenodo, though in principle, we'd like to have everything there, because it gets DOI and it's fully visible. There's an XML community on Zenodo if you register. So they're all on our website. In fact, I put the website up here. Yeah, well, it's not the front page. Let's go to the front page. So this is the XML project. It's actually a very useful name, because if you put XML into Google, this is what you get. No one else seems to have coined the name. Like I was talking to someone yesterday about Quantix as a nuclear motion code. Turns out there are at least 5 companies in the world that think Quantix is a good name for a company, besides this guy's software, so it gets a bit more confusing. And we actually have spawned databases. So we have quite a few databases now. In fact, we have one more than listed here, because we've been generating new ones. But the main XML database is all I'm going to talk about here. So we have opacities, radiative lifetimes, high resolution data, photo dissociation data. We have a new one on atoms, which is there but not publicly visible, and just writing one on cooling functions. But the main database is these molecular line lists. And we have not quite 100 molecules here. And I think we've got to find a better way of organizing them. It was fine when we had 20 molecules organizing it like this, but it's now getting a bit tedious. So I don't know. Anyone got a favorite molecule you want to look at? Any offers? Sorry? Do we have a... It's just a molecule, someone. Sorry? Carbon sulfide, CS. Yep. Okay. Interesting choice for cultural reasons. I think I've only had one Indian master's student. She did carbon sulfide. Lady called Gitu Fawaz. I have to be slightly careful. I've had lots of ethnically Indian masters and undergraduate students because there are plenty of them living in London. But she was Indian national who came to UCL to do the master's degree. So here we have CS, and you can see there are quite a few isotopologues here. Sulfur has quite abundant sub-isotopologues. So there's sulfur 32, which is spin 0, is the normal one, but 34, 33, 36 are also around, and 34 is several percent of sulfur, so you get it quite naturally on Earth. If we go into the main isotopologue, which is normally the first one listed, sorry. You get various options here. There's actually cross sections which are not the line list, but then you get two types of line lists: a photo dissociation line list from another group, actually from UGAMOP, which is stood for University of Georgia Atomic and Molecular Opacities, and it's a project which is not running anymore, but they had quite a lot of interesting historic data, so we captured it for our website. And then we have this JNK line list, and I can't remember what it was called, JNK, which is our recommended line list. So you go to the JNK line list, and then we have metadata, and we'll find out. Anyone ever use JSON? Yeah? It's a data formatting language. Oh, right, fine. If you have a nice plugin like my computer does, this comes out nicely set out in lists and colors and color-coded and whatever, but it's basically human readable. So you have ways of defining the molecule, including formal ways called INCHI keys, but also chemical formula. So the INCHI is a nice readable formula. Mass in Daltons, which you may call atomic mass units, but nowadays they're called Daltons. Point group, formula, 12 carbon, 13 isoslug, number of atoms, irreducible representation, etc., etc. Explaining what all those funny quantum numbers are all defined in here. Presence of pressure broadening. So basically all the metadata you want to know to do with the data. We originally, the other one is just in our, I pressed the wrong one. I pressed the def file. Did I? No, did I press the JSON one? No, I did press the JSON one. There was originally our own format, and then we went to a JSON one. If we're nice people, we have the spectroscopic model. So you can see Guido Pulvals was the person who did this. In this particular case, it was pre-Duo days. She used Level, the code written by Bob Leroy. We tell you the version. We have an input file. The idea is you can go away and just regenerate it. And it's useful for other people, but frankly, it's useful for us because we want to make a better one. It's quite useful to know where you started from last time. So it's just good practice. Then we have a picture of what the spectrum looks like at 2 temperatures. So actually, at our group meetings, which we have once a week on Tuesday, so it's Wednesday today, it was yesterday, we have a game. Has anyone ever played a game called Wordle, which was developed during, it's actually developed by a British guy who lived in America for his wife or his girlfriend. And it's, yeah, as I'm seeing a few nods. So we play a game called Spectral, where we get this, and we have to guess what the spectrum is. And you guess the atoms, and you can get, obviously, green if it's the right atom, orange if it's the right row of the column of the periodic table, or red if it's wrong. And we get 5 guesses, so it's like Spectral, but for that, and it just makes people get everyone in the idea of interpreting spectra. Normally they come from our database, but just occasionally someone sends me a spectrum and says, "Do you know what it is?" And certainly, I think that's only happened once, and we have 100% success. We sat there and we worked out what it was, which is aluminium oxides, it turned out. So you can see here that at room temperature 300 Kelvin, you get these rather sharp. These are simply, and this is a log scale. Yeah, it's rather aggressive log scale. So they are dropping by an order of magnitude for each of these vibrational overtones. So we've got the rotational spectrum, Vibrational fundamental, first overtone, second overtone, third overtone, fourth overtone. When you're up at 2000 Kelvin, the thing is looking much more continuous. It's still not completely continuous. And you've got two Life's good, apparently. Yeah. Right, so A and B, it's a good question. So those of you who studied these things will know actually there are three Einstein coefficients, A, B, and C. C is the one for stimulated, and we don't worry about that normally because we're not doing laser experiments. But A and B have a simple mathematical relationship between them. So if you know A, it's just degeneracy factors to give you B. So we store A's, and then we have formulae for emission, we have formulae for absorption. I think the one I gave you there was actually absorption. So we don't need to store the B's separately because they're related to the A's. It's a simple answer. And I could say everyone does A's, so we do A's. That's true. I also like A's because of I told you there's a physical interpretation to do with lifetimes. So if you're calculating things and you want to store numbers, it's very useful to have ones that have some meaning to you because occasionally you screw up. And if you don't understand the numbers, you carry on and you think they're perfectly okay, and they're not, they're garbage. So if you have something which actually has some sort of physical interpretation, you look at it and say, that can't be right, I've done something wrong here, and then you can go and look at it. But if it's just a random string of digits, it doesn't mean anything to you. So I like A's because they have a nice, simple physical interpretation, and I can look at them and say, these are right or these are not right. So there we are, we've got it back again. So you can see that at a higher temperature, it's much broader. And interestingly, it's broadened one way. So there are two effects for the broadening. Your side screens are not coming on very well, but anyway. Maybe they're coming. There are two effects for the broadening. One is the obvious one that you get more rotational lines, should get broader. The less obvious one, which actually is causing this asymmetry, is you get hot bands. So when it's at 2000 Kelvin, you don't just start from the V equals 0 level, you start from the V equals 1 level, V equals 2, and they're all slightly shifted downwards, so you get absorption on the left-hand side. So you get this sort of characteristic feature. And then by the time you're up here, it's almost continuous. But it's very weak. So I did tell you we get some up. These are actually cross-sections in centimeters squared per molecule. So a big cross-section, 10 to the minus 19, it's not huge, but it's fairly typical, centimeters squared per molecule. A barn is, I think, 10 to the minus, that's meters. I think it's 10 to the minus 16 centimeters, so this is about 0.1 of a barn, I think. But, you know, we're down here where it's flat, we're down at 10 to the minus 31, we're down at 12 orders of magnitude. It probably doesn't matter very much at that point. So let's carry on. So then we have the line list. And interesting, we have a README file. I have to say that's probably good practice, but we don't always have README files. I will do in a minute. Carbon monoxide is not ours, but I'll show it you. I have a student working on carbon monoxide at the moment, having fun and games. Come on, why is this not opening? Have we lost? No, yeah, we've lost the internet, I think. Sorry, that was the effect of the power cut. Can you log us on again? Sorry? Oh, right, it's 55 minutes. Oh, okay, fine. We'll wrap up in a minute. That's good. I might finish this quickly after the break. Finally, at least for me last night, the one thing that didn't go down was the internet when we had the power cuts. The internet stayed working. Right, there we are. So that's our README file explaining everything that's in there. So for instance, it gives the nuclear spin statistics, which I was struggling to understand for formaldehyde earlier. But you can see that it's for carbon 12, sulfur 32, it's 1 because they're both spin 0. But when you get to sulfur 33, that's spin, obviously a spin 3 half system because the nuclear spin degeneracy is 4. So it gives all the nuclear spin degeneracies, gives you the partition function in the range you calculated, gives you the format of the states file, gives you the format of the trans file, and if we go down a bit, tells you what else is there in terms of pressure broadening files, and where we get the level at 9 input. Now I have to say, we have not, this is a very early line list, and we've not been quite so good at keeping up all the documentation like that. I don't think on many of the other line lists you'll find a documentation file like that. And then we have the actual line list, which is a states file. And these are all B-zipped, so I'm hoping this computer is going to open them. It is doing good things. Oh no, I have to look at it in an app store. That's a bit annoying. Well, you've seen what this looks like. I already showed you. So that's the states file I showed you for formaldehyde. These are very small because it's a small line list. This states file is 120 kilobytes. The line list itself is 2 megabytes. Probably has a few tens of thousands of transitions in. That's, by our standards, that's very small. So that's CS. I had a quick request for CO. Vaguely similar, except it isn't, because actually CO is an external line list we took from somewhere else. So lots of isotope logs of CO. I think there are 12 of them. Hytran used to have a 1-digit key for the isotopes. Actually, sorry, it's 12 is CO2. I think how many there are there? The less. So you used to have a 1-digit key for the isotopes, and CO2 broke it, and they had to go to hexadecimal and start calling them A, B, C to fit them into 1 digit. But anyway, if you go to the main isotope log again, it's got several line lists there. We always have a recommended one, so there are three line lists here. We recommend LI 2015, and we also have cross sections for it, and then we have photo dissociation. Those are actually experimental. So we go to the recommended line list, and we have the JSON file, which will be presumably similarly gobbledygook like that, but it tells you this. It's very similar to CS, so it's not going to be wildly different. Spectroscopic model, which is interesting because we don't normally have that if it's an external thing, but we do have it here. So we have the input file, and that's for something different. That's the quadrupole spectrum we calculated. So those are quadrupole intensities, but we do. This is the normal dipole line list comes from Hytran. It's not our one. And then we have our famous picture. Again, looking vaguely similar, except for CO, we went up to higher temperature because CO is a very strongly bound molecule. You get it in atmosphere. The sun has CO in it. For instance, not just sunspots, the actual sun has CO in it. In fact, at low temperatures, solar temperatures and below, the nature of a star is determined by CO. So if you have oxygen and carbon in a star, the first thing it does is form CO. And then if you have any oxygen, if you have more oxygen than carbon, you get M dwarfs, which have water and titanium oxide in them. If you have more carbon than oxygen, you get carbon stars. They tend to have lots of molecules, HCN, carbon-2, carbon-3, methane, if they're cold enough. We all know that organic chemistry is complicated. That's even true in stars. And if you get carbon equals oxygen, you get a whole special class of stars. Anyone know what they are? S-type stars, which have all sorts of strange molecules like zirconium oxide and other things that are prominent in their spectra. And they're rather rare, but they're very interesting. So we did CO up to probably more than 5. Well, we didn't do, we took it. It's up to more than 5,000 Kelvin because it's important. And again, we have a transitions, a states. So right, we have transitions, normal dipole transitions, E2, E1 is dipole, E2 it's electric, and then the order of the moment. So dipole is first order, quadrupole is second order. We have a quadrupole transition as well. Line list, so we have both a dipole and a quadrupole transition list. The references they came from, which are not us, Gang Lee, who nowadays is some guy getting me doing metrology, but in those days was working for Hytran doing line lists. And then we have a partition function. Now here we only have the ground state. Electronically excited states of CO are really important. There's a huge amount of experimental data on it. Amazingly, there are no line lists. So that's what my PhD student is slaving on at the moment. So if you come back in 2 to 3 years' time, there should be a rather different page full of electronic spectra as well as rotation vibration spectra. Okay, I think I've overrun probably for coffee time. So anyone got any quick questions before we break? We took a slight detour on the XML line list. I probably have a couple of slides still to do on the other thing we'll do after coffee, and then we'll go into the tutorial session. Okay? So see you in 15 minutes, which is, what's the time now? So yeah, quarter to 4. Okay?